Light is the fastest thing there is. You learned that early, and it holds. Nothing in the universe outruns a beam of light, which crosses the gap from the moon to your eye in about 1.25 seconds. That speed can feel like a kind of freedom, a way for the whole cosmos to stay in touch. Tonight we're going to follow it somewhere quieter and stranger. The universe is expanding, and far enough out, it carries galaxies apart faster than their light can ever close the distance. Most of the galaxies in a long exposure of the night sky are already beyond our reach forever, and little by little, they are slipping out of sight as well. That is the trap hidden inside the speed of light, and it leaves one quiet thought to carry through everything ahead. What is it like to live in a cosmos that is slowly closing around us? Light is the fastest thing there is. Nothing in the universe moves quicker than a beam of light crossing empty space. It travels at a little under 300,000 kilometers every second, fast enough to circle the Earth more than 7 times in the time it takes to say the word. When you flick on a lamp, the room fills with light so quickly that the delay is far too small for you to feel. That speed is woven into nearly everything you know about the sky. It is why the sun looks like it sits right there above the trees, why the stars seem fixed in their places, why the night feels close and reachable. You learned the number early, in some classroom or some book, and it has held up ever since. Every careful test agrees on it. The speed of light in a vacuum is one of the steadiest, most reliable facts we have, so dependable that the world's scientists eventually built the meter itself around it. Since the year 1983, the speed of light has not been a thing we measure at all. It is a fixed value we agreed upon, and the length of a meter follows from it. The number stopped being a discovery and became a foundation. We tend to think of that speed as a kind of generosity. Light is the messenger that lets the whole cosmos stay in touch with itself. The warmth of the sun, the glow of distant stars, the faint smudge of a galaxy through a telescope. All of it reaches you because light is quick enough to carry the news across enormous gaps. A speed that high feels like a promise that nothing is truly out of reach. Given enough patience, the thinking goes, light will eventually arrive from anywhere, and so anywhere can be seen. Tonight we're going to follow that beam of light somewhere quieter and stranger than the classroom version of the story. We're going to take the most generous fact in physics and watch it turn, very gently, into a limit. Because the same finite speed that lets you see the sun also sets a hard edge on what you will ever see at all. Light is fast, but it is not instant. It takes time to cross space, and space, it turns out, is not holding still. There is a cost buried inside that famous number, and it is easy to miss because it only shows up at the larger scales, far beyond the sun and the nearby stars. Out there, among the distant galaxies, the finite speed of light stops being a convenience and starts being a wall. It draws a boundary around what can reach us, and the boundary is slowly closing. For now, hold on to the simple version. The speed of light is the cosmic top speed, the quickest any signal, any influence, any glimmer of information can travel. It is the same in every direction, and for every observer, no matter how fast they move. That sameness is the rock the rest of modern physics is built upon. Keep it in mind, because everything strange that follows grows out of that one steady rule. The story ahead is about distance and time and the quiet trap that appears when you combine a finite speed with a universe that refuses to sit still. It begins with something you do every clear night without thinking about it, the simple act of looking up. That ordinary act is stranger than it seems, and it is where we turn next. When you look up at the night sky, you're not seeing the universe as it is. You're seeing it as it was. Every point of light arriving at your eye left its source some time ago, and it has been travelling ever since. Because light moves at a fixed speed, the farther away a thing sits, the longer its light has been on the road, and the older the picture you receive. The sky is not a window onto the present. It is a record of the past, layered by distance. Start close to home. The moon hangs about 380,000 kilometres away, so its light reaches you in a little over 1 second. You see the moon as it was barely a moment ago, which is near enough to now that it hardly matters. The sun is farther. Its light takes about 8 minutes and 20 seconds to cross the gap. If the sun were somehow switched off, you would carry on in full daylight for those 8 minutes, unaware, because the last of its light would still be arriving. Step out past the sun, and the delay grows quickly. Light from Jupiter takes around 40 minutes to reach us when the planet is far in its orbit. The nearest star beyond the sun, Proxima Centauri, sits more than 4 light-years away, which means its light has travelled for over 4 years before touching your eye. You're seeing that star not as it is tonight, but as it was when light left it years ago. The same is true of every star in the constellations. Some of them are so distant that their light set out long before you were born. Go farther still, and the past deepens. The bright band of the Milky Way is light gathered from across our own galaxy, much of it tens of thousands of years old. The Andromeda Galaxy, the most distant thing most people can see without a telescope, lies about 2.5 million light-years away. The faint oval you can spot on a dark autumn night is 2.5 million years old. You're looking at light that left Andromeda when our earliest human ancestors were just beginning to walk the African plains. This is the quiet truth folded into stargazing. To look out into space is always to look back into time. There is no way around it, because no signal can travel faster than light, and light needs time to cross distance. The deeper you peer into the cosmos, the further back you see, until you are watching events that finished long ago. Telescopes turn this into a kind of time machine. The Hubble Space Telescope and the James Webb Space Telescope are built to gather light that has crossed billions of years, so that pointing them at the faintest, most distant galaxies is the same as looking far into the early history of the universe. The faintest smudges in their deepest images show galaxies as they were when the cosmos was young, so there is no single snapshot of the universe that you could ever take. The light from nearby reaches you fresh, while the light from far away is ancient, and it all arrives mixed together in the same glance. The night sky is a collage of many different moments, sorted by distance. That layering of time by distance is the first hint of the trap ahead. If the speed of the light limits how quickly we learn about distant things, then the size and behaviour of the universe will decide what we can ever learn at all. To go further, we first need to know that famous speed precisely, and how anyone ever pinned it down. For most of human history, people assumed light was simply instant. It seemed to appear everywhere at once. Strike a flame and the whole room brightens with no delay you could ever notice, so it was natural to think light took no time to travel. The great thinker Aristotle held that light had no speed at all, that it was a presence rather than a journey. Even Johannes Kepler, who unlocked the orbits of the planets, believed light crossed any distance instantly. The first real crack in that idea came not from a beam of light on Earth, but from a moon of Jupiter. In the year 1676, a Danish astronomer named Ole Rømer was working at the Paris Observatory, carefully timing the moon Io as it circled the giant planet. Io disappears behind Jupiter and reappears on a steady schedule, like a clock ticking out in space. Rømer expected those eclipses to come at perfectly regular intervals. Instead, he found something odd. When the Earth in its orbit was moving closer to Jupiter, the eclipses of Io arrived a little early. When the Earth was moving away, they arrived a little late. The pattern matched the changing distance between the two planets. Rømer understood what this meant. The light carrying the news of each eclipse had farther to travel when Earth was far from Jupiter, and so the news arrived later. Light was not instant after all. It had a speed, and the extra distance added a measurable delay. From the size of that delay, Rømer made the first real estimate of how fast light moves. His value came out lower than the modern figure, partly because the size of the solar system was not yet well known, but the achievement was enormous. For the first time, someone had shown that light takes time to cross space, and had put a number to it. A moon hundreds of millions of kilometres away had become a tool for weighing the speed of a sunbeam. Others sharpened the measurement over the centuries that followed. In the 1800s, the French physicists Hippolyte Fizeau and Léon Foucault measured the speed of light right here on Earth using spinning toothed wheels and rotating mirrors to time a beam over a known distance. Their results crept ever closer to the true value. Later, the American physicist Albert Michelson refined it further with mirrors set across mountaintops in California, earning a Nobel Prize for the precision of his work. By the 20th century, the speed of light in a vacuum was known to be about 299,792 kilometers every second. The measurements had become so exact and so trusted that scientists made a striking decision. In 1983, they fixed the speed of light by definition and redefined the meter in terms of it. From then on, the meter became the distance light travels in a tiny exact fraction of a second. The speed of light was no longer something to be measured and refined. It had become a fixed post that everything else is measured against. That fixed value carries a special weight in physics, and it is written with the letter C. It appears in equations that have nothing obvious to do with light, from the energy locked inside an atom to the behavior of gravity itself. It is not merely the speed of a sunbeam, it is the speed limit of the universe, the fastest that anything at all can travel. To understand why, we have to leave the laboratory behind and turn to the man who saw what that limit truly meant. By the early 1900s, the speed of light had become a puzzle that would not behave. Experiments kept finding the same strange result. No matter how the Earth moved through space, no matter whether you measured a light beam coming toward you or chasing after one, light always came out at the same speed. That should not happen. If you run toward an oncoming ball, it meets you faster. If you run away, it catches you slower. Light refused to play by those rules. It arrived at the same speed for everyone, always. A young clerk in a Swiss patent office took that stubborn fact seriously when almost everyone else tried to explain it away. His name was Albert Einstein, and in the year 1905 he built a new picture of space and time around it. He began from two simple ideas. The laws of physics are the same for everyone moving steadily, and the speed of light is the same for everyone too, no matter how they move. Those two ideas sound modest. Together they tore apart the comfortable notion that time and distance are fixed and universal. If light always travels at the same speed for every observer, then something else has to give, and what gives is time and space themselves. Einstein showed that a moving clock ticks more slowly than a still one, and a moving ruler shrinks along its direction of travel. These are not illusions or measurement errors. They are real features of the world, hidden from everyday life only because we never move anywhere near the speed of light. At ordinary speeds, the effects are far too tiny to feel. Near light speed, they become overwhelming. Out of this came the cosmic speed limit. As you push any object with mass to move faster, it grows harder and harder to speed it up further. The closer it creeps toward the speed of light, the more energy each extra bit of speed demands. To actually reach light speed would take an infinite amount of energy, which is another way of saying it can never be done. Light itself can travel at light speed only because the particles of light, called photons, have no mass at all. Anything with mass is forever held below that ceiling. The speed of light is therefore not just the speed of a sunbeam. It is the top speed of cause and effect, the fastest that any signal, any influence, any scrap of information can travel from one place to another. Nothing you could ever send, no message, no spacecraft, no push or pull, can outrun a beam of light. This single rule holds the universe together in a deep way. It means that distant events cannot affect us instantly. Whatever happens far away can only reach us at light speed or slower, and never sooner. Einstein's work has been tested for more than a century in particle accelerators, in the timing of fast-moving clocks flown around the world, in the steady ticking of the satellites that run the navigation in your phone. The satellites of the Global Positioning System must correct for these effects constantly, or they would lead you astray within minutes. Special relativity is not a guess. It is among the most thoroughly confirmed ideas in all of science. So we have a firm speed limit stamped on the cosmos, and a sky that shows us the past because light needs time to cross it. Both of those would be enough to make the universe strange, but there is one more ingredient discovered around the same time that turns this strangeness into a trap. The universe is not standing still, and the first to notice were astronomers staring at faint, smudged spirals of light. In the years before the First World War, a quiet astronomer at the Lowell Observatory in Arizona began studying faint spiral smudges in the sky. His name was Vesto Slipher. At the time, no one was sure what these spiral nebulae were. Some thought they were clouds of gas inside our own Milky Way, perhaps young solar systems in the making. Slipher set out to learn what they were made of and how they moved, using a technique that reads the light of an object like a fingerprint. That technique is called spectroscopy. When you spread starlight out into its colours, you find dark lines crossing the spread, each line marking light absorbed by a particular element. Those lines sit at known, fixed positions, like markings on a ruler. If the source is moving toward you, the lines shift toward the blue end of the spectrum. If it is moving away, they shift toward the red. The size of the shift tells you how fast the object is approaching or receding. It is the same effect that makes a passing siren drop in pitch as it speeds away, only carried by light instead of sound. Slipher pointed his instrument at the Andromeda spiral first, around the year 1912. Its lines were shifted toward the blue, which meant Andromeda was moving toward us, and quickly. That alone was a remarkable measurement for the time. But as he gathered more spirals, a strange pattern emerged. Nearly all of the others showed their lines shifted the other way, toward the red. One after another, the spiral nebulae were racing away from us, and at tremendous speeds, far faster than any star within the Milky Way had ever been seen to move. By the early 1920s, Slipher had measured the motions of dozens of these spirals. The great majority were fleeing. Some were retreating at hundreds, even more than 1,000 kilometers every second. Nothing in the known universe behaved like this. Stars in our galaxy drifted gently. These distant smudges were tearing away. Slipher had no framework to explain it, but he had carefully recorded the data, and the data were clear. Something about the spiral nebulae was deeply unusual. What Slipher could not yet know was that these spirals were not small clouds within our own galaxy at all. They were entire galaxies in their own right, vast islands of billions of stars lying far beyond the Milky Way. The proof of that would come a little later, when Edwin Hubble used the giant telescope on Mount Wilson in California to spot individual stars inside the Andromeda spiral and measure its true staggering distance. Once that was settled, Slipher's redshifts took on a much larger meaning. They were not the motions of nearby gas clouds. They were the flight of whole galaxies across the cosmos. Slipher's careful measurements became one of the most important sets of observations in the history of astronomy, even though his name is far less famous than those who built on his work. He had found the first solid clue that the universe is not a still, settled place. The galaxies are in motion, and overwhelmingly that motion is outward, away from us, in every direction we look. This raised a question that would reshape everything. Why should almost every distant galaxy be running away from our particular spot in space? It seemed to put us at the centre of some great expulsion, which sat uneasily with everything astronomers were learning about our ordinary place in the cosmos. The answer would come from a thinker who arrived at it not by looking through a telescope, but by following the mathematics of gravity to a conclusion almost no one was ready to accept. While astronomers were measuring the flight of distant spirals, a different kind of mind was working on the same puzzle from the opposite direction. His name was Georges Lemaître, a Belgian priest who was also a gifted physicist and mathematician. He came to the question not by gathering starlight, but by following the equations of Einstein's theory of gravity wherever they led, even when they led somewhere that made other scientists uncomfortable. Einstein had recently published his general theory of relativity, a sweeping description of gravity as the bending of space and time by matter. When Lemaître applied those equations to the universe as a whole, he found that they did not describe a static, unchanging cosmos. They described one that must be either expanding or contracting. A universe sitting perfectly still was not a natural solution. The mathematics wanted motion. This troubled many of the great figures of the age, including Einstein himself. Einstein had been so convinced the universe was eternal and unchanging that he had inserted an extra term into his own equations, a fudge meant to hold the cosmos still. Lemaître took the equations at face value instead. In the year 1927, he published a remarkable paper proposing that the universe is genuinely expanding, that the space between galaxies is growing, and that this expansion would make distant galaxies appear to recede. Then Lemaître went a crucial step further. He connected his expanding universe idea to the very redshifts that Schleifer and others had been measuring. He predicted that a galaxy's speed of recession should be proportional to its distance, meaning the farther away a galaxy lies, the faster it should appear to flee. He even worked out an early estimate for how steep that relationship should be, drawing on the data available at the time. He had both the theory and a testable prediction, years before the observations were widely accepted. His paper, written in French and published in a little-read Belgian journal, went almost unnoticed at first. The wider world of astronomy did not hear of it. When Lemaître met Einstein around that time and described his expanding universe, Einstein reportedly told him that his mathematics was correct, but his physics was abominable. The idea of a universe that grows, that has a history, that might even have had a beginning, was simply too radical for most scientists to embrace. Lemaître did not stop there. He reasoned backward in time. If the universe is expanding now, then in the distant past everything must have been closer together. Run the expansion far enough into the past and all the matter in the cosmos would have been packed into a single dense hot point. He called this starting state the primeval atom, a single original speck from which everything we see unfolded. This was the first real version of what we now call the Big Bang, proposed by a priest following the cold logic of equations to a beginning of space and time. For a while, Lemaître's vision sat on the edge of respectability, an elegant idea waiting for the evidence to catch up. The man had reasoned his way to an expanding universe and a cosmic beginning before the astronomical community was ready to believe either one. He had seen it coming. What turned his idea from a curiosity into a cornerstone was the work of the astronomer who could measure distances to galaxies with new precision, and who would lend his name to the very law Lemaître had predicted. With a great telescope on a California mountaintop, that astronomer was about to make the proportional flight of the galaxies impossible to ignore. On a mountaintop east of Los Angeles, the largest telescope in the world was about to settle one of the biggest questions in science. The Hooker telescope on Mount Wilson, with its mirror 2.5 meters across, gathered enough light to pick out individual stars inside the faint spiral nebulae. The astronomer using it was Edwin Hubble, a careful, ambitious observer who would put his name on one of the defining discoveries of the century. Hubble's first triumph was settling what the spirals actually were. By finding a special kind of pulsing star, called a Cepheid variable, inside the Andromeda spiral, he could measure its distance. Cepheids brighten and dim in a steady rhythm, and the speed of that rhythm reveals their true brightness, which in turn reveals how far away they sit. The answer placed Andromeda far outside the Milky Way. The spirals were separate galaxies, vast and remote. The universe was suddenly enormous, filled with countless other island galaxies beyond our own. With that settled, Hubble turned to a deeper pattern. He combined his own careful distance measurements with the recession speeds that Schleifer and others had gathered from redshifts. When he plotted distance against speed, a clean relationship appeared. The farther away a galaxy lay, the faster it was receding. A galaxy twice as far away fled roughly twice as fast. A galaxy 3 times as far fled roughly 3 times as fast. The recession speed rose in simple proportion to the distance. This proportional relationship became known as Hubble's law, published in the year 1929, though the underlying idea had been predicted by Lemaître 2 years earlier. In recent years, many astronomers have taken to calling it the Hubble-Lemaître law, to honour the man who saw it coming as well as the man who measured it. The steepness of the line, how much extra speed you gain for each step of distance, is called the Hubble constant, and pinning down its true value would become one of the great long-running quests of astronomy. The pattern carried a startling implication. At first glance, it seems to place us at the centre of everything, since galaxies in every direction are racing away from our particular spot. But Hubble's law actually points to something far less self-centred. If you imagine standing on any galaxy anywhere in the universe, you would see exactly the same thing. Every other galaxy would appear to recede from you, with the most distant ones fleeing fastest. There is no special centre. Every observer sees themselves as the still point in a fleeing crowd. A simple picture helps make sense of this. Imagine a loaf of raisin bread rising in the oven. As the dough swells, every raisin moves away from every other raisin. A raisin far across the loaf moves away faster than a near one, simply because there is more swelling dough between you and it. No raisin is the centre. The whole loaf is expanding, and each raisin sees all the others drifting away. The galaxies are the raisins, and space is the dough. So Hubble's measurements, built on Slipher's redshifts and matching Lemaître's prediction, revealed a universe in the act of expanding. The galaxies are not flying through space away from a central explosion. The truth is stranger and gentler than that, and getting it right matters for everything that follows. The galaxies are being carried apart by the swelling of space itself, and understanding that distinction is the key to the trap waiting at the edge of the visible cosmos. It is tempting to picture the expanding universe as a great burst, with galaxies hurled outward through space like shrapnel from a blast, all flying away from some central point where it all began. That picture is natural, and it is wrong. The galaxies are not racing through space. Space itself is stretching, and the galaxies are riding along with it. Getting this right changes everything about what the expansion means. Think again about the raisin bread rising in the oven. The raisins are not crawling through the dough under their own power. They are sitting still, more or less, while the dough between them swells and carries them apart. Each raisin stays put in its own little patch of dough. It is the growth of all the dough in between that pushes the raisins away from one another. The galaxies behave like those raisins. Most of them are not moving through space toward or away from anything. The space between them is simply growing. This is why the recession of distant galaxies is unlike any ordinary motion. When a car drives away from you, it travels through space, covering real ground. When a distant galaxy recedes, it may be sitting quietly in its own region of the cosmos, while new space steadily appears between you and it. The light it sends out has to cross that growing gulf, swimming upstream against the expansion the whole way. The galaxy is not fleeing through the universe is widening beneath it. The amount of new space added depends on how much space already lies between you and a galaxy. Across a short distance, between you and a nearby star, the stretching is so slight that it is utterly swamped by ordinary gravity and means nothing. Across the vast gulfs between galaxies, the stretching adds up. The more space there is between you and a distant galaxy, the more new space appears each second, and so the faster that galaxy seems to recede. That is exactly the proportional pattern Hubble found. Double the distance, and you double the amount of stretching dough, and so you double the recession speed. This stretching also explains the redshift in a deeper way than simple motion does. As light from a distant galaxy travels through expanding space, the space it is crossing grows while the light is in flight. The wave of light gets stretched along with the space, its wavelength pulled longer, shifted toward the red. The farther the light has travelled, the more expansion it has lived through, and the more its colour is stretched. The redshift is not only a measure of speed, it is a record of how much the universe has grown during the light's long journey. It also means the expansion has no centre and no edge that we could ever point to. There is no special place where the Big Bang happened and from which everything flew outward. The Big Bang happened everywhere at once, because in the beginning all of space was compressed together. As space expands, it expands at every point. Wherever you stand, you see the same outward flow, because the stretching is happening all around you and between you and everything else. This is the true shape of cosmic expansion, galaxies resting in their own patches of space, while the space between them quietly grows, carrying them apart without any of them truly moving. It sounds peaceful, and over short reaches it is, but this gentle stretching of space leads straight to one of the most counterintuitive facts in all of physics, a fact that seems at first to shatter the cosmic speed limit we just spent so long establishing. Here is a fact that sounds, at first, like a flat contradiction. There are galaxies in the universe that are receding from us faster than the speed of the light. They are rushing away so quickly that no signal could ever close the gap. And yet this breaks none of Einstein's rules. Both things are true at once, and resolving the tension reveals something subtle about what the cosmic speed limit really forbids. Recall what special relativity actually says. Nothing can move through space faster than light. A spaceship, a particle, a message, anything travelling from one point to another through space is held below the cosmic speed limit. That rule is firm and has never been broken in any experiment. But the recession of distant galaxies is not motion through space. It is the stretching of space itself, and that stretching is not bound by the same limit at all. This is the loophole written into the structure of the cosmos. The speed limit governs how fast things can move through space. It says nothing about how far space itself can grow. When you add up the expansion across an enormous distance, the total rate at which the gap widens can exceed the speed of light, even though nothing is actually travelling through space at superluminal speed. The galaxy at the far end is sitting still in its own patch of space, behaving perfectly lawfully. It is only the sheer amount of expanding space between us that makes the gap grow faster than light can cross it. Return to the raisin loaf one more time. Each raisin barely moves within its own bit of dough, but if the loaf were vast enough, and the dough were rising everywhere at once, then a raisin far enough away would be receding from you faster than you could ever walk toward it, no matter how quickly you moved. Not because that raisin is speeding, but because so much dough lies between you, all of it swelling at the same time. Stack up enough gentle local stretching across a great distance, and the total adds up to something faster than light. The recession speed of a galaxy grows steadily with distance, following Hubble's law. Near galaxies recede slowly, farther ones recede faster, and beyond a certain distance the recession speed crosses the speed of light. Every galaxy past that distance is being carried away faster than light, simply because there is so much expanding space between us and them. There is no wall, no sudden boundary in the expansion itself. The speed just keeps climbing with distance until it passes the speed of light and keeps right on going. This is why the expanding universe is so much stranger than a simple explosion. In an explosion, debris flies outward through space, and nothing could exceed light speed. In an expanding universe, space grows everywhere at once, and the apparent speed of recession has no ceiling. A galaxy can recede at twice the speed of light, or 10 times, given enough distance between us and it. None of it violates relativity, because none of it is motion through space. This fact carries enormous consequences, and they are not comforting. If a galaxy is receding faster than light, then light leaving it now may never reach us, because the gap is widening faster than the light can cross it. The expansion of space can carry a galaxy permanently beyond our reach. To make this concrete, we need to find the exact distance where recession reaches the speed of light, the place where the gentle stretching first becomes a barrier. That distance has a name, and it marks the next step in the story. There is a specific distance in the expanding universe where the recession speed reaches exactly the speed of light. Inside that distance, galaxies recede slower than light. Outside it, they recede faster. That boundary is called the Hubble sphere, and the distance to it is the Hubble distance. It is one of the most useful markers in cosmology, and also one of the most misunderstood. You can find this distance from Hubble's law itself. The law says recession speed grows steadily with distance, by a fixed amount for each step farther out. So there must be some distance at which the recession speed has climbed all the way up to the speed of light. With the current best measurements of the expansion rate, that distance comes out to roughly 14 billion light years. A galaxy sitting about 14 billion light years away is, right now, being carried away from us at almost exactly the speed of light. It is easy to assume this must be the edge of what we can see, the wall beyond which everything is lost. After all, if a galaxy is receding faster than light, surely its light can never reach us. But the truth is more delicate than that, and the Hubble sphere is not a simple cutoff. We can in fact see many galaxies that lie well beyond it, galaxies whose light is reaching us right now, even though they are receding faster than light. This sounds impossible, and untangling it reveals how strange the expanding universe truly is. The key is that the expansion rate is not fixed for all time. The Hubble distance itself changes as the universe evolves. A beam of light leaving a distant galaxy can be losing ground at first, swept backward by space expanding faster than light around it. But as the universe grows and the expansion rate shifts, the Hubble sphere can widen out past that struggling beam of light. Once the light finds itself inside the Hubble sphere, it can finally begin to make real progress toward us. A photon can spend billions of years being carried away before the tide turns and it starts the long swim home. So the Hubble sphere is not a fixed prison wall, it is a shifting line, and light can cross it from the far side under the right conditions. Some of the light arriving in our telescopes tonight comes from galaxies that were receding faster than light when that light first set out. The photons clawed their way across the gap over billions of years, sometimes losing ground before gaining it. The galaxies we see at the greatest distances were, and in many cases still are, receding from us faster than light. This means the simple intuition fails. The Hubble sphere is real and important, but it does not by itself mark the edge of the visible universe, nor the edge of what we can ever reach. It is the line where recession reaches light speed today, a snapshot of one moment in an evolving cosmos. The true boundaries of what we can see and what we can touch are set by different, deeper limits, and they do not sit at the same place. What the Hubble sphere does tell us is that the universe is far larger and far stranger than the simple, light travel time picture suggests. If galaxies can recede faster than light, and their ancient light can still reach us, then the universe we observe must stretch much wider than its age in light years would imply. That puzzle of a cosmos somehow broader than its own age is where we turn next. The universe is about 14 billion years old. Light travels 1 light year per year, so you might reasonably guess that the farthest we could possibly see is 14 billion light years away, the distance light could have covered since the beginning. The real answer is much larger. The edge of the observable universe lies about 46 billion light years away in every direction. The cosmos we can see is more than 90 billion light years across, far wider than its age in light years would allow. Reconciling these numbers reveals just how much the expansion of space changes everything. The reason for the gap is that the universe has been expanding the entire time. Light has been travelling through it. Imagine light setting out from a distant region long ago near the beginning of the cosmos. That light has been travelling toward us for billions of years. But while it travelled, the space it had already crossed kept stretching behind it, and the region it came from kept being carried farther away. By the time the light finally arrives, the place that emitted it is now far more distant than the light's simple travel time would suggest. Picture it like walking along a road that keeps stretching while you walk. You set out from a town and walk steadily toward your destination. But the road itself is being pulled longer, so the town behind you ends up much farther away than the number of steps you took. Light crossing the expanding universe faces exactly this. It covers a certain travel distance, but the source it left behind has been swept much farther out by the stretching of space in between. So when we say a galaxy's light took 13 billion years to reach us, That 13 billion light-years is only the distance the light travelled. The galaxy that sent it is now much farther away than that, because space expanded throughout the journey. The most distant light we detect set out from regions that are now around 46 billion light-years away. That present-day distance is what defines the size of the observable universe. This boundary, the farthest distance from which light has had time to reach us since the beginning, is called the particle horizon. It marks the present-day location of the most distant matter we could possibly observe. Everything inside it is potentially visible, given a good enough telescope. Everything beyond it has not had time to send light to us yet, because the universe is not old enough for that light to have completed the trip. It is worth holding the numbers side by side to feel how strange they are. A universe not quite 14 billion years old, observable out to 46 billion light-years in every direction, spanning more than 90 billion light-years from one edge of our view to the other. The age and the size do not match in the simple way you would expect, and the mismatch is entirely the work of expanding space-carrying distant matter, ever farther out while its ancient light crawls toward us. And the observable universe is almost certainly not the whole universe. It is only the part close enough for light to have reached us so far. Beyond the particle horizon, the cosmos very likely continues, perhaps far beyond, perhaps without end. We simply cannot see it, because its light has not had time to arrive. Our view is a sphere centered on us, bounded not by the edge of reality but by the speed of light in the age of the cosmos. To read the story written in that ancient light, we need to look more closely at what the stretching does to the light itself and what its colour tells us. When we look at the light from a distant galaxy, the single most useful thing we can measure is how far its colour has been shifted toward the red. That shift, the redshift, is the master key of cosmology. It tells us how far away a galaxy is, how long its light has travelled, and how much the universe has grown since that light set out. A great deal of what we know about the cosmos is read from this one number. Recall how the shift comes about. As light crosses expanding space, the space it travels through grows while the light is in flight. The wave of light stretches along with the space, its wavelength pulled longer. Longer wavelengths of visible light look redder, which is why we call it redshift. The more the universe expanded during the light's journey, the more its wave was stretched, and the larger the redshift we measure when it finally arrives. This makes redshift a direct readout of cosmic stretching. A galaxy with a redshift that doubled the wavelength of its light is showing us light from a time when the universe was half its present size. A galaxy whose light has been stretched to 3 times its original wavelength is showing us the cosmos when it was a third of today's size. The redshift is not just a speed. It is a measure of how much smaller the whole universe was when that light began its trip. Reading the redshift is reading a moment in the history of the cosmos. This is why redshift and looking back in time are so tightly bound together. A higher redshift means light that set out longer ago from farther away when the universe was younger and more compact. The faint, distant galaxies in the deepest telescope images carry the highest redshifts, their light so stretched that what left them as bright visible glow now arrives as faint infrared. The James Webb Space Telescope was built largely to catch this stretched out light, to see the most distant and earliest galaxies whose light has been pulled far into the infrared by billions of years of expansion. Astronomers describe redshift with a single number that captures how much the wavelength has been stretched. A small redshift means a nearby galaxy whose light left recently. A large redshift means a remote galaxy whose light has crossed most of cosmic history. As the number climbs, the light comes from ever earlier eras, from a universe that was smaller, denser, and younger. Push the redshift high enough, and you reach light from before there were any galaxies at all. There is a limit to how far this can go, and it is not a galaxy. As we look out to greater and greater redshifts, we are peering back toward the hot, dense beginning of the universe. Eventually we reach a point where the universe was so hot that it glowed, and was filled not with stars but with a fog of hot plasma. Beyond that, ordinary light cannot reach us, because the early universe was opaque, like the inside of a thick cloud. The most stretched light of all comes from the moment that fog finally cleared. That light is still arriving today, redshifted by an enormous amount, stretched so far that it is no longer visible light or even infrared, but faint microwaves. It is the oldest light in the universe, a glow that fills the entire sky and stands behind every galaxy we can see. It is the closest thing there is to a baby picture of the cosmos, and it forms the true backdrop against which the whole story plays out. Beyond the most distant galaxies, beyond the faintest smudges in the deepest telescope images, there is a wall of light. It surrounds us in every direction, filling the whole sky with a faint, even glow. This is the cosmic microwave background, the oldest light in the universe, and it is the closest thing we will ever have to a photograph of the cosmos in its infancy. It comes from a time before the first stars, before the first galaxies, when the entire universe was hot, dense, and glowing. To understand where it comes from, run the expansion backward. The universe today is cool and spread out. In the past it was smaller, denser, and hotter. Go back far enough, and the whole cosmos was a searing fog of particles, far too hot for atoms to hold together. Electrons roamed free, and light could not travel any distance without being scattered by them. The universe was opaque, glowing like the inside of a star, with light trapped in the fog. Then, about 380,000 years after the beginning, the universe cooled enough for a profound change. The temperature dropped low enough for electrons to settle onto atomic nuclei and form the first complete atoms, mostly hydrogen. Suddenly the fog cleared. With the free electrons gone, light could travel freely across space for the first time. The universe became transparent, and the light that was set loose at that moment has been travelling ever since. That liberated light is what we detect today as the cosmic microwave background. It left its source nearly 14 billion years ago, and it has been crossing expanding space the entire time. When it began its journey, it was the bright glow of a hot universe with a temperature of several thousand degrees, but the expansion has stretched it enormously over those billions of years, pulling its wavelength longer and longer, cooling the glow. Today that light arrives as faint microwaves, corresponding to a temperature of just under 3 degrees above absolute zero, the coldest temperature there is. This background glow was discovered by accident in the year 1965. Two researchers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna and kept picking up a faint hiss of noise they could not get rid of. It came from every direction in the sky, day and night, all year round. After ruling out every earthly source, including droppings from pigeons nesting in the antenna, they realized they had stumbled onto the afterglow of the early universe itself. The discovery earned them a Nobel Prize and confirmed that the cosmos had a hot, dense beginning. Later missions mapped this ancient light in exquisite detail. Satellites named COBE, then WMAP, then Planck, measured tiny variations in the glow across the sky, ripples of slightly warmer and cooler patches. Those faint ripples are the seeds from which all the galaxies and clusters later grew, the gentle lumps in the early universe that gravity slowly pulled together into the cosmic structure we see today. The baby picture contains, faintly, the outline of everything that would come. The cosmic microwave background is the farthest back we can ever see with light. It is the wall at the edge of the observable universe, the surface beyond which the cosmos is opaque to our eyes. Every galaxy, every star, every deep field image is set against this ancient glow. And this oldest light, this gentle afterglow of the beginning, will play a quiet and crucial role at the very end of our story. But first, the universe had one more surprise waiting, a discovery that turned the gentle expansion into something far more troubling. For most of the 20th century, astronomers thought they understood the basic fate of the expanding universe, even if the details were unsettled. The universe was expanding, that much was clear, and gravity, pulling on all the matter in the cosmos, should be steadily slowing that expansion down. The only real question seemed to be whether gravity was strong enough to eventually halt the expansion and pull everything back together, or whether the universe would coast outward forever, slowing but never stopping. Either way, the expansion was expected to be decelerating. Gravity could only pull inward, never push out. To settle which fate awaited the cosmos, two rival teams of astronomers set out in the 1990s to measure how much the expansion was slowing down. The plan was to look at extremely distant exploding stars and compare them with nearby ones. By measuring how the expansion rate had changed over cosmic history, they could weigh the universe and find its destiny. One team was the Supernova Cosmology project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and including Adam Riess. Their tool was a particular kind of stellar explosion called a Type Ia supernova. These explosions happen when a dense stellar ember called a white dwarf gathers too much matter and detonates. Crucially, they all explode with very nearly the same true brightness, which makes them superb cosmic distance markers. If you know how bright a thing truly is, and you measure how bright it appears, you can work out how far away it sits. Type Ia supernovae are bright enough to be seen across billions of light years, so they let astronomers measure distances deep into the cosmic past. Both teams gathered their distant supernovae and prepared to measure the slowing of the expansion. They expected to find that distant supernovae appeared somewhat brighter than a steadily coasting universe would predict, the signature of an expansion that had been faster in the past and was being reined in by gravity. That is not what they found. The distant supernovae were fainter than expected. They were farther away than they should have been if the expansion was slowing. The result pointed to something no one wanted to believe. The expansion of the universe was not slowing down at all. It was speeding up. Over the last several billion years, the stretching of space has been accelerating, carrying galaxies apart faster and faster. Both teams checked their work, hunted for errors, and arrived at the same stunning conclusion at nearly the same time in the year 1998. The discovery was so unexpected and so well confirmed by two independent groups that it reshaped cosmology overnight. The leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, shared the Nobel Prize in Physics in the year 2011 for the discovery. They had set out to measure how fast the cosmic expansion was slowing, and instead found it was speeding up. It was one of the great surprises in the history of science, and it forced physicists to confront the possibility that something unknown was actively pushing the universe apart, working against gravity across the whole of space. This was the twist nobody had planned for. The gentle, decelerating expansion everyone expected was an illusion. Something was driving the cosmos to expand faster and faster, an unseen influence filling all of space and overpowering the inward pull of gravity on the larger scales. No one knew what it was, they still do not, but it needed a name, and the name itself admits how little we understand it. The discovery that the universe is speeding up demanded an explanation, and the honest truth is that we still do not have a good one. Something is pushing the cosmos apart, overpowering gravity across the vast reaches between galaxies. Whatever it is, it fills all of space, and it acts like a kind of pressure-driving expansion ever faster. For lack of any deeper understanding, physicists gave it a placeholder name that captures our ignorance. They call it dark energy. The word dark here does not mean black or shadowed. It means hidden, unknown, invisible to us. Dark energy gives off no light and clumps nowhere we can point to. We know it exists only through its effect on the expansion of the universe, the steady acceleration measured in those distant supernovae. It is utterly unlike the matter and energy we are familiar with. Ordinary gravity pulls things together. Dark energy does the opposite, driving space to expand faster and faster everywhere at once. The most striking thing about dark energy is how much of the universe it makes up. When astronomers add up everything in the cosmos, the familiar matter, the stars and planets and gas and dust, accounts for only about 5% of the total. A further quarter or so is dark matter, an unseen substance that holds galaxies together with its gravity. The remaining share, roughly 68% of everything in the universe, is dark energy. The dominant ingredient of the cosmos is the one we understand the least. The stuff we can see and touch is a thin froth on top of a vast unknown. One leading idea is that dark energy is a property of empty space itself. According to this picture, even perfectly empty space is not truly empty. It carries a faint, constant energy of its own, woven into the fabric of the vacuum. As the universe expands and creates more space, more of this vacuum energy comes with it, so the push never dilutes. This constant energy of space is described by a term Einstein once added to his equations and later regretted, the cosmological constant. The very fudge factor he introduced to hold the universe still turned out decades later to describe something pushing it apart. But calling dark energy the energy of empty space only deepens the mystery. When physicists try to calculate how much energy the vacuum should contain, using the best theories of particle physics, they get a number vastly larger than what is observed, off by an almost unimaginable amount. The mismatch between prediction and reality is one of the worst in all of science. Something is badly missing from our understanding. We can measure dark energy's effect precisely, yet we cannot explain why it has the gentle strength it does, rather than a strength trillions upon trillions of times greater. So dark energy stands as one of the deepest open questions in physics. We know it is there. We know roughly how strong it is. We know it dominates the universe and drives the accelerating expansion. We do not know what it is, why it exists, or whether it will stay constant forever. This is a place where the science is genuinely unsettled, and the honest thing is to say so plainly. The most important force shaping the future of the cosmos is one we cannot yet name with any confidence. What we can do is follow the consequences. If dark energy keeps pushing as it does now, the accelerating expansion changes the long-term fate of everything. It transforms a universe that might have coasted gently outward into one that runs away from itself, faster and faster, without end. That change in fate is where the gentle stretching finally becomes a trap, and it begins with a simple shift from coasting to running. For billions of years after the beginning, the expansion of the universe behaved much as astronomers once expected. It was slowing down. In the early cosmos, matter was packed far more densely than it is today, and the combined gravity of all the matter acted as a brake on the expansion, steadily reining it in. The universe was still growing, but the growth was gradually losing speed, exactly the gentle deceleration that everyone had assumed would continue forever. Dark energy was always there in the background, a faint push spread through all of space. But in the early universe it was overwhelmed. With matter crowded so closely together, the inward pull of gravity easily won out over the feeble outward push of dark energy. So for the first several billion years, gravity ruled, and the expansion slowed. Had nothing changed, the universe might have coasted outward forever, slower and slower, or perhaps even halted and fallen back together. Then the balance tipped. As the universe expanded, the matter within it spread thinner and thinner. Galaxies drifted farther apart, and the average density of matter dropped. Gravity, which depends on how concentrated matter is, grew weaker across cosmic distances as everything became more dilute. But dark energy did not weaken. If it really is the energy of empty space, then as space expands and more of it appears, the total amount of dark energy only grows. Its push per unit of space stays the same no matter how much the universe spreads out. So there came a turning point, a moment when the thinning matter no longer had enough gravity to overpower the steady push of dark energy. the brake of gravity faded and the accelerator of dark energy took over. This crossover happened a few billion years ago, when the universe was a bit more than half its present age. Before it, the expansion was slowing. After it, the expansion began to speed up. The supernova teams caught the universe in the act, measuring distant explosions from the old slowing era and nearer ones from the new accelerating era. This shift from deceleration to acceleration is a profound change in the character of the cosmos. A decelerating universe is, in a sense, friendly. Light from distant galaxies has an easier time reaching us because the expansion it must fight against is weakening over time. Given enough patience, more and more of the universe would come into view. An accelerating universe is the opposite. The expansion it must fight against grows stronger over time, and the gap to distant galaxies widens faster and faster. Light has a harder and harder journey, and eventually for the most distant galaxies an impossible one. We happen to live not long after the turning point, in the early stretch of the accelerating era. The transition from coasting to running away is relatively recent in cosmic history, and its full consequences are only beginning to unfold. The universe has shifted gears from a gentle outward drift held in check by gravity to a runaway expansion driven by an unknown energy that grows in influence with every passing eon. This is the moment where the gentle stretching of space turns into something with teeth. As long as the expansion was slowing, the reach of light could keep growing, and the universe stayed open to us. Once the expansion began to accelerate, a new kind of boundary appeared, a line that light sent today can never cross. That line is the real trap hidden inside the speed of light, and naming it precisely is where the story turns from wonder toward something colder. There is a line drawn around us in the accelerating universe, and once something crosses to the far side of it, we can never reach it again. Not with a spacecraft, not with a radio signal, not with a beam of light sent at the full speed allowed by physics. This line is called the cosmic event horizon, and it is the real trap hidden inside the speed of light. It is not the edge of what we can see, it is the edge of what we can ever affect or ever be affected by for the rest of time. The cosmic event horizon is easy to confuse with the other boundaries we have met, so it helps to set them side by side. The particle horizon marks how far light has managed to travel toward us since the beginning. It is about the past, about what light has had time to arrive. The event horizon is about the future. It marks the farthest distance to which light leaving us now could ever travel, and the farthest distance from which light leaving now could ever reach us. One looks back, the other looks forward, and forward is where the trap lies. In a universe that was slowing down, there would be no such trap. As the expansion eased, the reach of light would keep growing, and given enough time, a signal sent from here could touch any galaxy at all. Patience alone would conquer any distance, but in an accelerating universe, the expansion does not ease, it strengthens, and that changes everything about how far a beam of light can go. Picture a photon leaving the Milky Way right now, aimed at a distant galaxy. It travels at the speed of light, the fastest anything can move. But the space between here and that galaxy is expanding, and in an accelerating universe, that expansion is speeding up. For a nearby galaxy, the photon wins. It outpaces the modest stretching and arrives. For a galaxy beyond a certain distance, the photon loses. The space ahead of it stretches faster than the photon can cross it, and the gap widens forever. The light travels on for eternity and never arrives. That certain distance is the cosmic event horizon. With dark energy as it stands, it sits at roughly 16 billion light-years away. Any galaxy beyond that line is permanently unreachable. A message we send today, travelling at light speed, will chase it across the void forever and fall ever farther behind. The galaxy is not behind a wall we could break through with a faster ship. No speed allowed by physics could ever close the gap because the gap grows faster than light itself. This is the cruel part of the trap. It does not slam shut with a sound or a barrier you could see. A galaxy crossing the event horizon looks no different in the moment. Its light keeps arriving for a long while, fading and reddening so gradually that nothing seems to change. But the crossing is final. Once a galaxy passes the event horizon, the last light it will ever send us is already on its way, and after that, silence. Nothing it does from then on can reach us, and nothing we do can reach it. So the accelerating universe carves the cosmos into two regions. There is the part we can still in principle touch, the galaxies inside our event horizon, and there is everything beyond, sealed off forever by expanding space. The trap is not that we cannot see these distant galaxies. We can. The trap is that we can see them while they are already gone. Here is the fact that follows, and it is a heavy one. The overwhelming majority of the galaxies we can see in the night sky are already beyond our reach. They sit outside the cosmic event horizon. We can observe them, study them, photograph them in long exposures, and yet there is nothing we could ever send that would arrive. No signal, no probe, no influence of any kind. They are visible and unreachable at the same time. The numbers are stark. The observable universe contains something like 2 trillion galaxies, spread out to the particle horizon some 46 billion light-years away. But the cosmic event horizon sits at only about 16 billion light-years. Everything between those two distances, the great bulk of the visible cosmos, lies in the zone we can see but never touch. By careful estimates, more than 90% of the galaxies we can currently observe have already crossed beyond our event horizon. Their light still reaches us, but we will never reach them. Think about what that means for any dream of crossing the cosmos. Suppose we built a ship that could travel at very nearly the speed of light, the fastest physics allows. We could reach the stars of our own galaxy. We could, in principle, reach the nearby galaxies bound to us by gravity. But for the vast majority of the galaxies scattered across a deep telescope image, even this perfect ship would never arrive. It would chase them forever as the expanding space between carried them away faster than the ship could follow. The destination would recede without end. This is not a limit of our technology. It is a limit written into the structure of space-time itself. No improvement in engines, no breakthrough in propulsion, no clever trick could overcome it, because nothing can travel through space faster than light, and the expansion of space outpaces light across those distances. The galaxies beyond the event horizon are as unreachable as it is possible for anything to be. They are not far in the way a distant country is far. They are far in a way that no journey can ever cross. It is worth pausing on how recently we learned this. Before the discovery of cosmic acceleration in the late 1990s, there was no firm event horizon of this kind. A coasting or decelerating universe leaves the door open. Given enough time, its reachable region keeps expanding to include more and more. It was only when we found that dark energy is driving the expansion faster and faster that the door was revealed to be closing. We learned, within living memory, that most of the visible universe was already lost to us, and the boundary is still tightening. As the acceleration continues, the event horizon does not grow to embrace more galaxies. It effectively shrinks in the sense that fewer and fewer galaxies remain within reach. One by one, the galaxies still inside our horizon are drifting toward it and across it, joining the vast majority already gone. The reachable universe is not filling up, it is emptying out. So when you look at a photograph of thousands of galaxies, you're looking at a crowd that has, for the most part, already left. They shine for us, but they are no longer ours to reach. To make the loss vivid, imagine trying to send them a message and follow that message out into the dark. Imagine we decided today to send a message to the universe, not a modest broadcast to nearby stars, but a signal aimed at everything, travelling outward at the speed of light in all directions, carrying whatever we most wanted the cosmos to know. Picture that wave of light expanding away from the Milky Way, sweeping outward year after year, reaching ever farther into the dark. How much of the universe would ever receive it? The answer is bounded by the cosmic event horizon. The message travels at light speed, the fastest anything can go. So the farthest it can ever reach is exactly the distance light can travel from here into the future, which is the event horizon itself, around 16 billion light years. Every galaxy inside that boundary could, in principle, receive our message someday, if it travelled long enough. Every galaxy beyond it never will. The signal will chase those distant galaxies forever, falling farther behind with each passing eon, and never close the gap. This means that the overwhelming majority of galaxies we can see would never get the message, no matter how long we waited. We could send it today, or 1 billion years ago, and it would make no difference to them. The expanding space between us and them grows faster than the signal can cross it. Our most patient, most powerful broadcast would wash outward, reach the galaxies near enough to be within the horizon, and then simply run out of universe it could ever touch. Beyond a certain shell around us, the cosmos is forever deaf to anything we say. There is a quieter version of this same truth that is even more humbling. Many of the galaxies we see in our deepest images would not receive a message we sent today, and we would not receive a message they sent today either. The communication has already become impossible in both directions. If some civilization in one of those distant galaxies were trying, at this very moment, to signal us, their message would never arrive. The window for any exchange between us closed long ago, sealed by the expansion of space, even though we can still see each other's ancient light. So the night sky is full of places we can watch but never speak to. We see their past, frozen in arriving light, while their present has already slipped beyond any possible contact. The cosmos is not one connected whole, where everything can, given time, reach everything else. It is breaking into islands, each able to communicate only within its own shrinking neighbourhood, cut off from the rest by walls of expanding space that no signal can ever climb. This casts the famous question of cosmic loneliness in a new and sharper light. People often wonder whether we're alone in the universe, but the accelerating expansion adds a crueler dimension to that question. Even if the cosmos teems with life, even if countless galaxies hold civilizations gazing up at their own skies, most of them are already beyond any hope of contact with us. We could not reach them, and they could not reach us, however much either side might wish it. The universe may be crowded and still leave each of us marooned. This is the loneliness built into the structure of space-time. Not the loneliness of an empty cosmos, but the loneliness of a full one whose pieces are sealed away from one another, and it deepens further when you realise what the light we see tonight is really showing us, because the galaxies in our images are, in a sense, already ghosts. When you look at a distant galaxy tonight, you're seeing light that left it long ago. We met this idea at the very beginning, the simple truth that to look out is to look back. But in an accelerating universe, that familiar fact takes on a darker edge. The galaxy whose ancient light you are admiring may have already crossed beyond the cosmic event horizon. The light is real and present, arriving in your telescope right now. The galaxy that sent it is, in every way that matters, already gone. Think about what this means. The light from a remote galaxy might have set out billions of years ago. While it crawled across the expanding void toward us, the galaxy itself was carried farther and farther away by the stretching of space. By the time the light arrives, the galaxy may sit well outside our event horizon, in the region we can never reach. We are seeing a portrait of where it was and how it looked in the deep past, but the living galaxy behind that portrait has slipped permanently out of contact. The image is a kind of ghost, light from something we have already lost. This is a strange and quiet sort of haunting. The galaxies in our deepest photographs are not necessarily gone in the sense of having been destroyed. Most of them are still out there, still full of stars, still turning. But they are gone to us. The connection between us and them has been severed by expanding space, and all we have left is the old light still in transit, the last messages from a time when contact was still possible. We are surrounded by the glow of places we can no longer reach, looking at a sky full of farewells. It deepens the meaning of every long exposure image of the cosmos. Those breathtaking fields of thousands of galaxies, each one a city of billions of stars, are in large part a gallery of the unreachable. The light is a record of a connection that has already lapsed. We can study these galaxies, learn their shapes and ages and compositions, and yet we are studying the past of things that have moved beyond our future entirely. The richer and deeper our images become, the more of this lost universe they reveal. There is something almost tender in it, if you let yourself feel it. The light has travelled for ages to reach you, faithful across an unimaginable gulf, only to arrive carrying news of a place you can never go. It is the cosmic version of starlight from a candle long since burned out, except that the galaxy is very likely still shining. It is not the galaxy that ended. It is the road between us that closed, while the light was still on its way. And the road is closing further every day. The galaxies still inside our event horizon are drifting toward it, and their light is reddening as they go. With each passing eon, more of the sky shifts from the reachable column into the column of ghosts. The living, contactable universe shrinks, and the gallery of farewells grows. We are watching, in extreme slow motion, the lights of the cosmos turn from companions we might have reached into memories we can only observe. To see how a galaxy makes that final crossing, we can follow a single one as it nears the line, and watch what its light does in the long ages as it slips away from us forever. Follow a single galaxy as it approaches the cosmic event horizon, and watch closely what happens to its light. The galaxy does not vanish in an instant. There is no flash, no sudden disappearance, no moment where it blinks out like a switched-off lamp. Instead, it fades in a long, gradual way, its light stretching redder and dimmer over enormous spans of time, until at last it slips below any hope of detection. The crossing is slow, silent, and absolute. As the galaxy recedes ever faster, carried outward by accelerating space, its light has to climb against a steepening expansion to reach us. Each wave of light that leaves the galaxy is stretched more than the wave before it, shifted further toward the red. The galaxy's colour slides from visible light into infrared, then into longer and longer wavelengths toward microwaves and beyond. Its brightness drops in step because the same stretching that reddens the light also spreads its energy thinner and thinner. The galaxy grows dimmer and redder together, on a curve that bends toward forever. There is a subtle effect woven into this fading that makes the ending especially gentle. As the galaxy nears the event horizon, time itself appears to slow for it from our point of view. The light from its final moments before crossing takes longer and longer to reach us, smeared out across vast stretches of our future. We never actually see the galaxy cross the line. Instead, we see it approach the horizon and freeze there, fading and reddening without limit, its last image stretched so thin and so far into the infrared that it eventually becomes undetectable. The galaxy is gone not with a departure we can witness, but with an endless dimming approach to a line it never quite seems to touch. In practice, the galaxy becomes invisible long before this drawn-out theoretical fade is complete. Its light shifts so far toward long wavelengths and grows so faint that no instrument could ever pick it out from the darkness. The photons arrive more and more sparsely, with longer and longer gaps between them, until they stop arriving in any way we could measure. For all practical purposes, the galaxy has left the observable universe, even though a few impossibly stretched, impossibly faint photons might in principle still be straggling in across the eons. This is how the accelerating universe takes its galaxies away. Not by destroying them, and not by hiding them suddenly behind a wall, but by stretching their light past the point of seeing. One by one, on timescales far longer than the present age of the cosmos, the galaxies beyond our local neighbourhood will follow this path. Each will redden, dim, slow and fade, sliding down toward the infrared and out of view, until the deep sky that now blazes with distant galaxies grows dark and empty. It is worth holding the timescale in mind because it keeps the wonder honest. None of this happens quickly. The galaxies we see tonight will remain visible for billions upon billions of years yet, fading so slowly that across all of human history so far, the change would be far too small to notice. The trap closes on a clock so vast that the cosmos will look much as it does now for an almost unimaginable span. But the direction is fixed and the ending is certain. The far future of the sky is darkness, arriving one faded galaxy at a time. That far future has a name and a shape, a final state the universe is drifting toward, and it is one of the loneliest pictures in all of science. If dark energy stays as it is, the universe is heading toward a particular long-term state, and physicists have a name for it. They call it a de Sitter universe, after the Dutch astronomer Willem de Sitter, who first worked out the mathematics of a cosmos dominated by a constant energy of empty space. It is a universe that expands forever at an accelerating rate, growing emptier and lonelier without end. It is, most likely, where everything is headed. In a de Sitter future, the accelerating expansion never stops and never slows. Space keeps stretching faster and faster, doubling in size over and over across fixed stretches of time. Anything not held together by its own gravity gets carried away and pulled apart by the relentless growth of space between. The distances between unbound galaxies grow without limit, and the cosmic event horizon settles into a fixed size around each observer, a permanent boundary beyond which nothing can ever be seen or reached. What makes this future so lonely is the way it isolates everything from everything else. Today the universe is richly connected. Light crosses between galaxies, and the sky is full of distant company. In the de Sitter future, that connection dissolves. Galaxy after galaxy crosses the event horizon and disappears from view, until each surviving island of matter is left alone in its own patch of space, surrounded by an empty, expanding darkness. Whatever lies beyond the horizon might as well not exist, for it can never again be seen or touched or known. This is not a violent ending. The de Sitter universe does not end in fire or collapse. It does not tear itself apart in a single catastrophe. Instead, it grows ever colder, ever emptier, ever more diffuse. The matter that remains spreads thinner across a swelling void. Stars burn out, and no new gas gathers from beyond to make more. The universe drifts toward a cold, dark, dilute stillness, the same picture extended forever, with the isolated remnants of structure marooned in an ocean of expanding nothing. There is a strange stability to it, which is part of why it is so haunting. A de Sitter universe is, in a sense, eternal and unchanging in its overall character. Once it settles into pure accelerating expansion, it simply keeps going, the same forever. There is no further drama, no new chapter, no turning of the wheel. Just endless expansion, endless cooling, endless thinning out, with each isolated island sealed inside its own horizon, unaware of and unreachable by all the others. The richness and connection of the present cosmos is a passing phase, giving way to a permanent, lonely calm. It is sobering to realize that the lively, crowded universe we know, with its 2 trillion galaxies woven into a vast cosmic web, is the temporary state, and the empty de Sitter loneliness is the lasting one. We live in the brief, bright youth of the cosmos, when galaxies still fill the sky and light still crosses freely between them. The long future is the quiet after, when the lights have gone out one by one and each survivor sits alone in the dark. Yet not everything is lost in this future. Some things stay. The relentless expansion carries away the distant galaxies, but it does not reach inside the structures that gravity binds tightly together. There is a circle of the cosmos that remains, that holds firm against the tide, and it is the part we will always call home. That enduring island is worth knowing, because it is what survives. Not everything gets carried away by the expanding universe. The relentless stretching of space pulls the distant galaxies beyond our reach, but it does not touch the things that gravity holds firmly together. Within a gravitationally bound system, the local pull of matter wins out over the gentle push of dark energy, and the structure stays intact. For us, the structure that will endure is the local group, the small family of galaxies to which the Milky Way belongs. The local group is a modest gathering by cosmic standards, a few dozen galaxies bound together by their mutual gravity, spread across roughly 10 million light-years. Two large spiral galaxies dominate it, our own Milky Way and the Andromeda Galaxy, each surrounded by a retinue of smaller companion galaxies. There is the Triangulum Galaxy, a third spiral, smaller than the other two. There are the Magellanic Clouds, the bright satellite galaxies that hang in southern skies, and there are dozens of faint dwarf galaxies orbiting the giants, the small change of the local cosmos. What binds this group together is gravity, and gravity here is strong enough to resist the expansion. The galaxies of the local group are not receding from one another in the way distant galaxies recede from us. They are held in each other's grip, orbiting and drifting and slowly falling together, immune to the stretching of space that carries off the rest of the universe. While the cosmic expansion pulls everything beyond the local group away, the group itself holds firm, a stable island in a dissolving sea. This is why the local group is the part of the universe that will always be ours. As the eons pass and the accelerating expansion sweeps the distant galaxies across the event horizon and out of sight, the local group will remain. Its galaxies will stay bound, stay visible to one another, stay reachable in principle by any traveller patient enough to cross between them. Whatever happens to the wider cosmos, this small neighbourhood endures, a lasting home against the tide of expansion. In fact, the local group will grow more tightly knit over time, not looser. Gravity continues to draw its members together, and over billions of years they are destined to merge. The Milky Way and Andromeda, the two great spirals, are already falling toward each other, and they will eventually combine into a single larger galaxy. The smaller members will be drawn in as well, until the whole local group settles into one vast island of stars, bound together for as long as the stars themselves endure. So the future is not entirely a story of loss. It is a story of a shrinking visible universe, yes, but also of a stable, enduring core that remains close and connected. We will lose the distant galaxies, the 2 trillion points of light scattered across the deep sky. We will keep the local group, the family that gravity holds. In the far future, that bound island of merged galaxies will be, for any observer within it, effectively the entire visible universe, alone in an ocean of empty expanding space. That coming union of the Milky Way and Andromeda is the next great event in our own local story, a slow-motion collision already underway. It was long described as a certainty, a fixed appointment in the deep future. But recent work has added a note of genuine doubt to that old certainty, and the honest version of the story now includes a real question mark. The Milky Way and the Andromeda Galaxy are drifting toward each other. We met this fact a moment ago, but it deserves a closer look, because it is the great coming event in our own corner of the cosmos, and because the story around it has recently changed in an honest and interesting way. Andromeda is the large spiral galaxy nearest to us, about 2.5 million light-years away, and for a long time astronomers spoke of its collision with the Milky Way as a settled certainty. The reason for expecting a collision is that Andromeda shows a blue shift, not a redshift. Almost every galaxy in the universe is receding from us, its light shifted toward the red. Andromeda is one of the rare exceptions. Its light is shifted toward the blue, which means it is moving toward us, falling inward under the mutual gravity binding the local group. Andromeda is approaching at something like 100 kilometers every second, a slow drift on human terms, but a steady, gravity-driven fall across the gulf between us. For years, the picture was vivid and definite. In about 4 to 5 billion years, the two great spirals would crash together, their stars sweeping past one another in a long, gravitational dance. Because the space between stars is so vast, almost no stars would actually collide. Instead, the two galaxies would pass through and around each other, tearing out long streamers of stars and gas before finally settling, over further billions of years, into a single merged galaxy. Astronomers even gave the future merged galaxy a name, sometimes called Milkomeda, blending the names of its two parents. But here the honest story requires a pause because the certainty has softened. Measuring whether Andromeda will truly hit us depends not only on how fast it approaches, but on its sideways motion across our line of sight. A galaxy moving straight toward us will collide. A galaxy with enough sideways drift will swing past instead, missing the head-on crash. That sideways motion is extraordinarily hard to measure across 2.5 million light-years, and recent studies, drawing on the most precise position data yet, have found that the sideways motion is uncertain enough to change the outcome. When researchers folded in this uncertainty, along with the gravitational tugs of other local group members like the Triangulum Galaxy and the Large Magellanic Cloud, they found that a direct collision in the next several billion years is no longer a sure thing. By some recent analyses, the chance of the two galaxies merging within the next 5 billion years is closer to a coin flip than a certainty. Over much longer spans, 10 billion years and beyond, a merger still looks likely, but the clean, confident picture of a collision on a fixed schedule has given way to something more genuinely open. This is a good example of how science stays honest with itself. For decades, the Milky Way and Andromeda collision was presented as fact, and it appeared in countless articles and videos as a certainty. Then better data arrived, and careful researchers were willing to say that the truth is less settled than they had thought. The galaxies may still merge, perhaps in 5 billion years, perhaps in 10 or more, or they may first swing past each other in a near miss before eventually falling together. The wonder is undiminished, and now it is wrapped in an honest uncertainty. Whatever the exact path, the local group will eventually draw together, while the rest of the universe recedes, and as it does, the wider sky will slowly go dark, galaxy by galaxy, in a process worth watching unfold. Step far enough into the future and watch the sky empty out. Not all at once, but gradually, over spans of time that dwarf the present age of the universe, the galaxies beyond our local group will redden, dim, and disappear from view. The crowded deep sky of today, blazing with 2 trillion galaxies in every direction, will thin and darken until the distant universe is simply gone from sight. The sky will wink out, one galaxy at a time. The process follows the path we traced for a single galaxy crossing the event horizon, now playing out across the entire cosmos. As the accelerating expansion carries each distant galaxy away faster and faster, its light stretches toward the red and fades toward the infrared. Nearer galaxies last longer. The most distant ones fade first, their already stretched light tipping past the point of detection soonest. Like lights going out across a vast city seen from a hilltop, the galaxies vanish in waves, the farthest first, the closer ones following over the ages. Put a rough clock on it, with the understanding that these numbers are vast. In something like 100 billion years, perhaps a bit more, the galaxies beyond the local group will have receded so far and redshifted so deeply that they become undetectable to any observer within our merged home galaxy. That is more than 7 times the current age of the universe, an almost incomprehensible stretch of future time. But it is finite, and it ends with a sky that holds only the stars of our own galaxy and nothing beyond. By that distant era, an astronomer looking out from within the merged remains of the Milky Way and Andromeda would see a single galaxy, their own, surrounded by perfect darkness. The deep field images that today reveal thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length would show nothing at all. The cosmic web, the grand structure of galaxies and clusters and filaments that fills the universe today, would be invisible, its light stretched away beyond any hope of seeing. the observable universe would have shrunk to a single island of stars adrift in an empty void. If you find this stretch of the story moving, and you want to keep wandering through the deep questions of the cosmos like this, you might subscribe so the next quiet journey finds you. There is a great deal more sky to walk through together, slowly, the way we have tonight. The fading of the distant sky is not a sudden loss, but an immense gradual dimming, far too slow to notice on any human timescale, yet utterly certain in its direction. Each galaxy that crosses the event horizon sends its last, most stretched light toward us, and then falls silent forever. Over the long ages, the count of visible galaxies drops from 2 trillion toward a mere handful, and finally toward one, our own bound island standing alone where once the whole crowded cosmos shone. This emptying of the sky is more than a melancholy spectacle. It has a consequence that reaches into the very possibility of knowledge, because the galaxies are not only beautiful, they are evidence. They are the data from which we learned that the universe expands, that it began in a hot, dense state, that it is built the way it is. When they vanish, that evidence vanishes with them, and that loss sets up one of the most unsettling ideas in all of cosmology. Imagine astronomers living in that far future, 100 billion years from now, gazing out from the merged galaxy that was once the Milky Way and Andromeda. They look up with the finest telescopes they can build, and they see only their own galaxy, a single island of stars surrounded by an empty, silent darkness. Beyond it, nothing. No other galaxies, no distant lights, no sign of any structure in the void. Their universe, as far as they can observe, is one galaxy, an endless black space. This grim future was spelled out clearly by the physicists Lawrence Krauss and Robert Scherrer in an influential study of the far future of cosmology. What Krauss and Scherrer pointed out is genuinely disturbing. Those future astronomers, looking out at an empty sky, would have no way of discovering the truths we know today. They could not learn that the universe is expanding, because there would be no distant galaxies whose redshifts reveal the expansion. They could not learn that other galaxies exist at all, because every one of them would have faded beyond detection. From their vantage point, the cosmos would appear to be a single static galaxy, sitting in an eternal, unchanging void, and every observation they could make would seem to confirm that false picture. Worse, these future scientists would not be making any mistake of method. They could be brilliant, careful, rigorous, doing everything right. The problem is not in their reasoning, but in their evidence. The data that would tell them the truth, the light from distant galaxies and the glow of the early universe, would simply be gone, stretched away beyond any possible instrument. They would draw the best conclusions available from what they could see, and those conclusions would be profoundly wrong, not through any fault of their own, but because the universe had hidden the evidence. This is what Krauss and Scherrer call the end of cosmology, not the end of the universe which rolls on, but the end of our ability to understand it from observation. The window during which the expansion, the beginning, and the structure of the cosmos are visible is a limited one. It is open now. It will not stay open forever. As the distant galaxies fade and the early light slips away, the universe erases the clues to its own history, leaving future observers with a sky that lies to them by omission. It is a strange and humbling thought that knowledge itself can have an expiration date written into the laws of physics. We tend to assume that the truth, once discoverable, stays discoverable, that any sufficiently advanced civilization could in principle learn what we have learned. The accelerating universe says otherwise. There are truths about the cosmos that are knowable only during a certain era, and outside that era, they are sealed away. The universe does not preserve its own evidence indefinitely. This reframes our present moment in a remarkable way. We are not living in a typical time for observing the cosmos. We are living in a privileged window, when the sky is still full of galaxies and the evidence of the universe's nature is still on display. The future will be blind to what we can plainly see. and the most important piece of evidence to vanish will be the very first light, the afterglow of the beginning itself, which is fading toward erasure even now. Of all the evidence that the far future will lose, the most precious is the oldest light of all, the cosmic microwave background. We met this ancient glow earlier, the afterglow of the hot young universe, released when the cosmos first turned transparent some 380,000 years after the beginning. It fills the whole sky today, a faint and steady microwave hum, and it is the single strongest piece of evidence that the universe began in a hot, dense state. In the far future, it too will be gone. The cosmic microwave background fades for the same reason the galaxies do. As the universe expands, this ancient light is stretched along with space, its wavelength pulled ever longer. Today it arrives as microwaves, already stretched from its original fiery glow to a whisper just above absolute zero. As the accelerating expansion continues, the stretching will deepen. The microwaves will become radio waves of longer and longer wavelength, weaker and weaker, until eventually their wavelengths grow so vast that no conceivable instrument could detect them. The afterglow of creation will redshift its way into undetectable silence. There is a further problem that seals the loss. To detect a wave, you need an instrument at least comparable in size to the wavelength you're trying to catch. As the cosmic microwave background stretches toward wavelengths of enormous size, detecting it would require an antenna larger than any practical structure, eventually larger than a galaxy, eventually larger than the observable universe itself. Long before that point, the ancient light becomes not just faint, but fundamentally impossible to capture. The first light of the cosmos passes beyond any physical means of detection. When the cosmic microwave background fades from reach, the future loses its clearest proof of the Big Bang. Today, this glow is the smoking gun of the hot beginning. Its existence, its temperature, its faint ripples all testify that the universe was once small, hot, and dense, and has been expanding and cooling ever since. Strip it away, and one of the central pillars of our understanding disappears. Future observers would have no direct evidence that the universe ever had a hot, dense origin at all. The same fate awaits other subtle clues. The relative amounts of hydrogen and helium in the universe, forged in the first minutes after the beginning, are another fingerprint of the hot origin. But over immense spans of time, as stars process matter and the bound galaxy churns its gas through generation after generation of stars, even this chemical signature will be muddied and obscured. The pristine record of the early universe, written in the proportions of the lightest elements, will be overwritten by the long work of stars. Clue by clue, the evidence of the beginning erodes. So the universe is, slowly and silently, erasing the story of its own birth. The distant galaxies that reveal the expansion will fade. The ancient afterglow that reveals the hot beginning will redshift into nothing. The chemical traces of the first minutes will be obscured by stellar processing. Every independent line of evidence that points back to the Big Bang is, on a long enough timescale, scheduled for erasure. The beginning becomes unknowable, not because it did not happen, but because every trace of it is carried beyond reach. A future built on what remains visible would therefore tell a very different story about the cosmos, a story that is wrong in nearly every important way, yet perfectly consistent with all the evidence that survives. Picture the cosmology that those far future scientists would construct, working honestly from the only evidence left to them. They would see a single galaxy, their own, sitting in an empty and unchanging void. No other galaxies, no redshifts to reveal expansion, no ancient afterglow to hint at a hot beginning. From this evidence, the natural conclusion would be that the universe is static, eternal, and small, a lone island of stars that has always existed and always will, surrounded by infinite empty space. It would be a false eternity, a wrong picture that fits every fact they could gather. This false cosmology would not be a result of sloppy thinking. It would be the best and most reasonable interpretation of the available data, A static, eternal universe of one galaxy is exactly what the evidence would suggest once the expansion and the distant galaxies and the cosmic afterglow have all faded from view. The future scientist would have no reason to suspect that their galaxy was once one of 2 trillion, or that the whole cosmos had erupted from a hot, dense beginning billions of years before, or that space had ever been expanding at all. Their honest science would lead them confidently to the wrong answer. There is a real irony in this, because the false picture they would reach is close to what many thoughtful people believed in our own recent past. Before the discoveries of the 20th century, before Slipher's redshifts and Hubble's law and the cosmic microwave background, a static and eternal universe was the default assumption of most astronomers. Einstein himself initially built his equations to describe such a universe, adding a term specifically to hold it still. The far future would, in a sense, return cosmology to that older view, except that this time the static universe would be a genuine illusion, with the truth hidden rather than simply undiscovered. What makes this so unsettling is what it implies about the relationship between evidence and truth. We naturally assume that careful observation leads toward correct understanding, that a sufficiently advanced and honest science will converge on the way things really are. The accelerating universe breaks that comforting assumption. It shows that the evidence available at a given time can be fundamentally incomplete, and not in a way the observers could detect or correct for. The future astronomers would have no clue that their universe was lying to them, no anomaly to chase, no loose thread to pull. The illusion would be seamless. It raises a quiet and uncomfortable question about our own moment. If the far future can hold a confident, consistent, and completely wrong picture of the cosmos, how certain can we be that our own picture is complete? Perhaps there are truths about the universe that have already faded beyond our reach, evidence that vanished in some earlier era, leaving us with our own seamless illusions. We have no way to know what we cannot see. The lesson of the false eternity is humility, a reminder that what we can observe is not guaranteed to be the whole of what is true. But there is another side to this, and it is the one worth carrying forward. If the far future is blind, then the present is uniquely sighted. We happen to live in the rare era when the evidence is still here, when the expansion is still visible, when the afterglow still glows and the galaxies still fill the sky. We can see the truth that the future will lose. That privilege is the heart of where this story has been heading all along. We live in a remarkable window of time, not a typical moment in cosmic history, but a privileged one, a span during which the universe still displays the evidence of its own nature. The expansion is visible in the redshifts of distant galaxies. The hot beginning still echoes in the cosmic microwave background. The sky is still full of 2 trillion galaxies, whose light tells the story of a cosmos that grew from a dense, fiery start. All of this is on display right now, and all of it is temporary. Consider how the timing works out. The universe is about 14 billion years old. The era during which distant galaxies and the cosmic afterglow remain observable stretches to perhaps 100 billion years, after which the accelerating expansion will have hidden them away. So the window for seeing the true nature of the cosmos, open near the beginning and closing in the far future, is a limited stretch of cosmic time. We have arrived while it is open. The evidence that future observers will never have is for us simply there in the night sky, waiting to be read. There is something almost too fitting in this timing. If intelligent observers had arisen only in the far future, after the galaxies had faded and the afterglow had stretched away, they could never have discovered the expanding universe or the hot beginning, no matter how brilliant they were. The evidence would have been gone. We arrived early enough to catch it. The cosmos laid out its history in light, and we appeared during the brief age when that history can still be seen and understood. This casts our scientific moment in a poignant light. The great discoveries of modern cosmology, the expansion, the Big Bang, the accelerating universe driven by dark energy, are not just triumphs of human cleverness, they are also gifts of timing. We happened to look up during the window when the answers were visible. A civilization born too late would gaze at an empty sky and conclude, reasonably and wrongly, that it lived in a small, static, eternal universe. We were born in time to know better. It also means there is a kind of responsibility folded into this moment, though a gentle one. We are among the observers who can still see the whole picture. The knowledge we gather now, the maps of the cosmic web, the measurements of the ancient light, the careful charts of the expansion, are records of truths that will not always be observable. In some sense, we are witnesses to a cosmos that is slowly drawing a veil over its own past, and what we learn and preserve now is a record of how things really were, made during the age when they could still be seen. The window will not close for an unimaginably long time, far beyond any human concern, far beyond the lifetime of the sun, far beyond almost anything we can meaningfully plan for. There is no urgency in the practical sense, but there is meaning in the recognition. We live in the lit room of cosmic history, with the doors to the past and the future both still ajar, able to see in both directions before the slow closing begins. And within this window, the work is far from finished. Even now, with the evidence still bright around us, the central numbers of cosmology are not fully pinned down. There is a live and unresolved argument about exactly how fast the universe is expanding, and it is one of the most interesting puzzles in science today. Even within our privileged window, with the evidence laid out around us, we have not finished reading it. One of the most basic numbers in all of cosmology, the rate at which the universe is expanding, is the subject of a genuine and unresolved disagreement. The number is called the Hubble constant, the steepness of the relationship between a galaxy's distance and its recession speed that Hubble first measured. And right now, two careful ways of measuring it give two different answers that stubbornly refuse to agree. The first method works outward from the nearby universe. Astronomers use objects whose true brightness they understand well, such as the pulsing T-Fied variable stars and the Type Ia supernovae we met earlier, to build a ladder of distances reaching out into the expanding cosmos. By comparing those distances with the measured redshifts, they read off the expansion rate directly. This local method gives a Hubble constant of roughly 73 kilometers per second for each megaparsec of distance, a megaparsec being a little over 3 million light-years. The second method works from the early universe instead. The cosmic microwave background, that ancient afterglow, carries in its faint ripples a detailed record of the conditions in the young cosmos. By measuring those ripples precisely, as the Planck satellite did, and feeding them through our best model of how the universe evolves, astronomers can calculate what the expansion rate should be today. This early universe method gives a smaller number, around 67 kilometers per second per megaparsec. The two answers are close, but not close enough. The gap between roughly 73 and roughly 67 might sound small, but both measurements have become so precise that the difference is far too large to be brushed aside as mere error. Each method has been checked, refined, and cross-examined for years, and the disagreement has not gone away. It has, if anything, grown sharper as the measurements improved. This stubborn mismatch has a name. Astronomers call it the Hubble tension, and it is one of the liveliest problems in physics today. Nobody yet knows what the tension means. One possibility is that some subtle error still lurks in one of the methods, a flaw not yet found. But as both sides have been scrutinized so heavily, many researchers suspect the answer is more interesting. The mismatch may be a sign that our standard model of the universe is missing something, some new ingredient or unexpected behavior in the early cosmos, in dark matter, or in dark energy itself. The Hubble tension may be a crack through which new physics is showing. This is worth dwelling on, because it is a reminder that cosmology is a living science, not a finished story. We have a powerful and successful picture of the universe, expanding from a hot beginning and accelerating under dark energy. Yet even the basic expansion rate is still being argued over, with two excellent measurements pointing to two different values. The trap at the edge of the cosmos is real, and the broad story is firm. but the details are still being worked out, honestly and openly, by people measuring the sky as carefully as they can. The Hubble tension concerns how fast the universe expands today. An even deeper question hangs over the future, and it has stirred fresh excitement very recently. The question is whether dark energy, the force driving the whole story, is truly constant, or whether it might be changing. Everything we have said about the far future rests on one crucial assumption, that dark energy stays constant, an unchanging energy of empty space pushing the cosmos apart at a steady strength forever. If that assumption holds, the future unfolds as we have described, toward isolation and an empty sky. But we do not actually know that dark energy is constant. It is the least understood thing in the universe, and recent measurements have raised the genuine possibility that it might be changing over time. This question has come alive very recently, driven by a major survey called DESI, the Dark Energy Spectroscopic Instrument, which is mapping the positions of millions of galaxies to trace how the expansion has behaved across cosmic history. In results released in recent years, the DESI collaboration found tentative hints that dark energy may not be perfectly constant after all. The data suggest, though they do not yet prove, that the strength of dark energy might have been slightly different in the past and could be evolving as the universe ages. The hints are not yet certain, but they are strong enough to take seriously. If dark energy is changing, the long-term fate of the universe is back in question, and several very different endings become possible. Should dark energy weaken over time, or even reverse into a pull, the accelerating expansion might slow, halt, or turn around, sparing the cosmos the lonely de Sitter future and perhaps drawing it back together. The trap at the edge of the cosmos might loosen rather than tighten. The empty sky we forecast might not be the ending after all. Should dark energy instead grow stronger, the future could turn far more violent than a gentle fading. In one dramatic scenario called the Big Rip, an ever-strengthening dark energy would eventually tear apart not just galaxies but everything within them. First the galaxies would be ripped from one another, then individual galaxies pulled apart, then solar systems, then planets and stars, and finally atoms themselves, all shredded by an expansion growing without limit toward a single catastrophic moment. In that future, the universe ends not in cold isolation but in a final tearing apart of all structure. Between these extremes lie gentler possibilities, futures where dark energy shifts mildly, and the cosmos coasts toward an ending less stark than either the Big Rip or the pure de Sitter loneliness. The honest truth is that we do not know which path the universe will take, because we do not know what dark energy truly is, or whether it will hold steady. The DESI hints have reopened a question many thought was settled, and the coming years of observation will test whether dark energy is the steady constant of the simple picture, or something more surprising. This is the living edge of the science, where the wonder and the uncertainty meet. We have learned enough to see the trap clearly, to know that the accelerating expansion is carving the cosmos into isolated islands and slowly hiding the universe from itself. But the deepest question, whether that process will continue forever, soften, or end in a final tearing, remains genuinely open. The fate of everything hangs on the nature of a force we cannot yet name, and we are only beginning to measure whether it changes. Whatever the ending turns out to be, the present remains what it is, and that is where this long journey returns at last, to the simple sky overhead. So we come back to where we began, to the simple act of looking up at the night sky. Light is still the fastest thing there is. It still crosses the gap from the moon to your eye in a little over a second, still carries the warmth of the sun across 8 minutes of empty space, still brings the glow of distant galaxies after journeys of millions or billions of years. The fact that opened this story has not changed. What has changed is what you know it to mean. You know now that the same finite speed that lets you see the cosmos also draws a boundary around it. The universe is expanding, and far enough out it carries galaxies apart faster than their light can ever close the distance. Most of the galaxies in a long exposure of the night sky are already beyond our reach forever, visible as ancient light yet sealed away by expanding space. And little by little, across spans of time too vast to feel, they are slipping out of sight as well, reddening and dimming toward an empty future sky. This is the trap hidden inside the speed of light. Not a cruelty meant for anyone, just a consequence of the way space, time, and light fit together in an accelerating universe. The cosmos is slowly closing around every observer in it, sealing each island of galaxies inside its own shrinking horizon. The crowded, connected universe we know is the brief youth of things, and the long future is a quiet isolation, with the evidence of the whole grand story fading beyond any future eye. And yet here is the gentle turn at the end. We live in the window when it can all still be seen. The galaxies still fill our sky. The ancient afterglow of the beginning still glows faintly in every direction. The expansion is still written in the redshifts, the history of the cosmos still legible to anyone who looks with care. We arrived early enough to read the story before the universe finishes hiding it. That is not a small thing. It is a rare and quiet privilege to live in the lit room before the slow closing of the doors. So the trap is real, and so is the gift. The light reaching you tonight has crossed an expanding cosmos to arrive, faithful across unimaginable distances, carrying news of places you can never go, and a beginning that will one day be unknowable. It is a farewell and a record at once. The universe showing you its truth in the brief age when truth is still visible. Every distant galaxy in the sky is a message from a connection that is quietly lapsing, delivered while there is still someone here to receive it. There is no need for sorrow in this, only a kind of attention. The closing is unimaginably slow, far beyond any human time, far beyond the life of the sun. For us, and for an almost endless run of those who come after within our bound island of galaxies, the sky will look much as it does now, full and deep and luminous. The trap closes on a clock so vast that tonight, and for a very long succession of nights, the universe remains open and bright overhead. So go outside when the sky is clear and look up at that old and faithful light. It travelled a long way to reach you, through a cosmos that is gently carrying its sources beyond your grasp. You are seeing the universe in the one era when it can still be truly seen. Let that quiet wonder settle and stay with you, under a sky that is still for now full of light.